So now that we have introduced the concept of primitives and where they fit within the Qiskit ecosystem, in this video we will discuss the primitives available to us within the Qiskit package, which are the StatevectorSampler and the StatevectorEstimator. So to do that, let's take a look at some examples where we compare how would we provide the inputs and read out the outputs to these primitives with respect to what we would do with, let's say, the basic simulator. So let's start by just importing the quantum circuit class and both the StatevectorSampler and the StatevectorEstimator, and for comparison, also the basic simulator. Let's create a simple 2-qubit circuit, and then let's define our simulator object using the basic simulator, and then a sampler object using the StatevectorSampler. Now, as before, we can define a job for our simulator by just doing simulator.run, passing the circuit, and the number of shots. Now, typically we want to transpile this circuit before doing this, but we know that these two gates are within the basis set of the simulator, so we should be okay without transpiling. And now let's see how we will do this for the sampler. So let's assume that we just have to use the exact same format. So we do sampler.run, pass the circuit, and then the number of shots. Unfortunately, this will result in an error, which is really not that easy to understand. The issue with the sampler is that we can't just simply pass a quantum circuit. If you recall, the input to the sampler has to be a list of primitive unified blocks or pubs. So unlike the regular simulator in which you can just pass a quantum circuit, here you have to really specify a list. So you need to pass this quantum circuit inside brackets. Now, as we discussed before, pubs consist of circuits, parameters, and number of shots. Since this circuit has no parameters, and we have specified the number of shots outside of this list, we can pass only the quantum circuit, and this will work okay. We will look at more complex examples in a minute where we actually use the full format for the pubs. So after this, for our simulator, we will obtain our results by simply doing job simulator.result. Now, luckily for our sampler, this works in the same way. We extract the results using this .result method. And then if we wanted to get, let's say, the counts for the simulator result, all we would do is use this .getCounts helper method, and then we can print our result. Now for the sampler, if we try to do the same thing, we're going to get an error. So we need to figure out what's the format of this result that we get out of the sampler. So one thing we can do is first just print that result, and we see that this is a primitive result, which has inside a pub result. So this is our result for our primitive unified block, and we see that this consists of two elements, one which is a list with the pub result, and then this metadata object which doesn't have anything. So to extract our pub result, we actually need to index the 0th element within this primitive result. That will give us the pub result we need. Now this pub result has two attributes. One is this data result, and then the metadata, which has the number of shots. So if we now do this .data, we get the data bin with the results we want. Now, how do we extract those results? Well, it seems that this has an attribute called C. So let's print that and see what we get. So this gives us a bit array. So if we go to the Qiskit documentation and look at what a bit array is, well, it says it's an object that contains a block of data that represents an array of bit strings. But if we look at some of the methods it has available, we can see that it does indeed have a getCounts method we can use to extract our counts. So here we can then use the .getCounts to get our result. So let's put this side by side with what we would do for the simulator just to see how they compare. So before, our result object would have the getCounts helper method to extract the results. But now this is a more complicated structure where we need to index whichever result we want to extract. And we'll talk more about this in a minute. Then we need to get the data, then this .c, and then get counts. But what is this C? Well, it turns out that this is the name of our classical register. So if we scroll up here, by default, Qiskit names classical registers as C. Now, this is only true if we don't specify explicitly a classical register here with a specific name. That would change if we do so. Also, if instead of defining the number of classical bits here, we remove this and use instead the measure all function, which actually adds those classical registers for us for whichever number of qubits we have, the name of the register changes. It's no longer C. By default, Qiskit names this in a different way. So if we were to execute our simulation again and try to extract those results from the sampler, we will get an error saying that data bin does not contain attribute C. We'll have to change this C for the correct name of that register. Now, personally, I think this is a huge problem because having the name of an attribute depend on what you name a register is very problematic when writing code. There is no easy way for us to write code where the name of this will change automatically if we were to assign a different name to our register. So personally, I think this definitely needs to be changed by, for example, storing the results in a dictionary where you just extract those results by finding the key of that dictionary that would have the same name as the register you define. But giving that name to an attribute is a bad idea. But in any case, this is the way we extract results right now. So now let's look at a slightly more complicated example. Let's define a circuit that now has a parameter in it. So in this case, it has this angle theta, which can vary. If we were to run a simulation for different values of this parameter using the basic simulator, we'll have to first create a list with the parameter values, and we would have to iterate over that list and assign the different values to different circuits. So in this case, I'm just creating a for loop and storing 3 different circuits for each of these 3 parameters and appending them to that list. So if, for example, I draw the circuit in the first position of this list, we'll get the circuit with the pi over 3 angle, right? And if I draw, for example, the one for the 0th position, then I'll get the pi over 4. Same for the second position is the pi over 2. And then with this list of circuits, we could just transpile it using the simulator backend, and we can pass it to that simulator, that the list itself, not each individual circuit, to extract the results. And then to get each separate result, we will iterate over the number of circuits we have, which is the same as the number of angles. And we will get the counts for each of these by using the number corresponding to that particular circuits inside our getCounts helper method. So what I'm doing here is I'm storing the 3 different results for the 3 different circuits in this counts simulator list. So if I print that, then we can see the 3 results right here. So in summary, with the simulator, we would have to generate a list of 3 separate circuits and pass those to the simulator to get the results. In the case of the sampler, what we can do is what we discussed in the previous video, which is pass the parameters inside a primitive unified block. So same as we did before, we do sampler.run, and we need to pass a list of pubs, right, of primitive unified blocks, and I'm passing those as tuples. So this tuple has the circuit, which still has the parameter theta. So this is not any of the circuits in which I already replaced the parameter for a value. This is the circuit is still with this theta. And the list of angles that are the parameters that internally the sampler will replace into the circuit. So what the sampler is doing is this process I did here is doing it automatically for me. And then I specify the number of shots separately, and then I can get the results. Now to extract them, I would follow a similar process to what I did for the basic simulator. I just iterate over the different circuits. So just remembering that the way we extract that data is a lot more complicated, right? Now I need to index the 0th element of our result, get this data attribute, then the name of the register, and then use this get counts with the number of the circuit corresponding to the angle that we have assigned. So I'm just iterating over the 3 possible angles and appending that to a list. And if I run that, then I can get my 3 separate results. Now what happens if I don't iterate over the 3 separate circuits, but I just try to do this get counts without passing the circuit number? What the sampler does is it actually adds all 3 separate values for the 3 circuits. Now, there might be some situations in which this is useful, but this is extremely important to keep in mind and something we need to be very careful about, right? Because we might be thinking that this would do something similar to what you get with the basic simulator, which is actually get the entire list for the 3 results. I know above we used a for loop to extract them, but with the old simulators, you could just extract the list immediately. Whereas with the sampler, you do need to extract one by one. If you don't, then it adds up all the results. Now in this example, we only passed 1 pub to the sampler, but we can pass more than 1. So we can do the same thing we did before. We pass a pub with that parameterized circuit and a list of angles. But we can also pass, let's say, the circuit we had defined above that doesn't take any parameters. So let's go back up here. So this circuit, right? And let's do this for now where we actually pass the 2 classical bits to it instead of using the measure all function. So if we now execute this, we get the results for the sampler. And in a similar way, we would extract the results for the first pub by indexing the 0th result here. And again, doing .data, the name of the classical register that has our results, .get counts. And here we would just pass, since we have 3 different angles, we pass the number for the circuit that we want the result for. So this will be for the first element in that list or the second circuit, right? If we do 0 here, we get it for the first circuit. But what if we want to extract the results for this second pub? Well, what we would do is here index the first element of the results. So what happens if we do this? Well, we get an error because that first circuit doesn't have a classical register with this name. We will have to change the name here to C. And that would give us the result for that particular circuit. Now, in the previous video, I mentioned that pubs are composed of a circuit, a set of parameters, and you could also specify separate shots for each of the pubs. So if we run this here, you can see that we get counts now for the second circuit where the total sum is 100. And if we take a look at for the first set of circuits, then that would still sum up to 1024. So if we specify the number of shots outside of the list of pubs, then all the pubs will be executed with the same number of shots, or we can explicitly specify the shots for each of the pubs we want to run. Now, something extremely important to keep in mind about the StatevectorSampler is that because the backend this uses is the Statevector class from the Quantum Info package, we can't execute circuits with mid-circuit measurements using this type of primitive. So for example, if we have this type of circuit where we perform a measurement and try to apply a gate based on that measurement, if we use the StatevectorSampler, we will get an error that says we cannot handle mid-circuit measurements. Now, unfortunately, there is a bug in the code that if you, for example, have a mid-circuit measurement, but on a separate register, as long as you only have 2 measurement blocks, instead of giving you this error, it would actually produce the incorrect results, which is very concerning. So here, for example, we'll see that this won't give us an error. And if we try to extract the results, we see that we're getting with equal probability state 0, 1 and state 1, 1, when we should be getting for this type of circuit actually equal probability for state 0, 0 and state 1, 1. But in any case, you should always just avoid trying to use mid-circuit measurements when using the state vector sampler. Now for the version 1 primitives, we used to be able to get more meaningful data other than just the counts. We were able to extract quasi-probability distributions of our results using a different method. Now, for the version 2 primitives, for some reason, this has been removed. So if you wanted to calculate probabilities, you will have to take the count, so use a separate function to do that. So now let's move to the estimator. So for the estimator, as we mentioned before, we also need to pass as an input primitive unified blocks, so pubs, but they have a slightly different format. So if you recall, we need to pass a circuit, we need to pass the observables, the parameters if our circuits are parameterized, and then the precision to which we want to obtain an expectation value. Now, something really important here is that when using the StatevectorEstimator, our circuits cannot have measurement blocks at the end. So when we define our circuit, let's say we're going to define the same one we had above with the parameter theta, we can't add any measurements here. Otherwise, we'll get an error. So then we can define a list of observables. So here I have 2 observables, which I've defined using the sparse-poly operator class from the Quantum Info module. Now, I won't go into the details of what this means. I might do this in a separate video later on, but the idea is that here you just have 2 observables that you want to calculate expectation values with respect to the circuits. So then we specify an estimator object using the StatevectorEstimator, and we run it in a very similar way to what we did with the sampler. We do estimator.run, and then we provide a list of pubs. So in this case, our pub consists of the circuit we define above, right? This one right here. Our list of observables. So here we have a list of 2 observables. A list of parameters. So here we're passing 3 parameters, the same we had defined above. So pi over 4, pi over 3, and pi over 2. And then the precision. And if we run this, we can then extract our result in a very similar way. So we get our result here, and then we use the 0th index because we only have 1 pub here. If we have more pubs, then we will go 1, 2, and so on to address each of the results of all the separate pubs in this list, right? But here we're just using 0 for the first one, then again .data. But here, instead of having to call the name of a classical register, which we don't even have in our circuits, we just do .evs, which stands for expectation values. And then we get an array that has 2 lists here. The reason we have 2 is because we pass 2 separate observables, each with 3 separate values. And the reason we get 3 separate values is because we have 3 parameters for our circuit. Pi over 4, pi over 3, pi over 2. So we get a total of 6 results for 2 observables, and each of these gets 3 results for each of the parameters we passed. So that sums it up. So as you can see, the way we use the primitives is very different from what we used to do before with the air simulator or the basic simulator, but we get a lot more functionality and don't have to do extra work to, for example, organize the way circuits are going to be passed with certain parameters. The primitives will do this for us, and in the case of the estimator, then it would generate all the circuits needed to calculate the expectation values using certain observables. So we don't have to do that manually anymore. And then it will provide the right results in the right order. So in the next video, we'll look into the sampler and estimator from the Qiskit IBM runtime, which are the classes that would allow us to do exactly the same we did here, but specifying IBM's quantum processors as the backend. Now the good thing is that the format of the inputs and the outputs is exactly the same as what we have here. So that would allow us to run simulations and then take the results and compare them with hardware by using a similar way to execute things.